Welcome to AI Podcast. I'm Alex, and today we're unpacking a paper titled Mixture of Agents Enhances Large Language Model Capabilities. Here's the bottom line up front. If you let several language model agents draft answers and then ask a strong model to synthesize those drafts, you can get consistently better answers without any additional training. The authors call this setup Mixture of Agents, or MOA, and it achieves leading results on widely used instruction-following benchmarks at the time they tested it, with a lighter, cheaper variant that still performs impressively.
I'm Maya. So the idea is don't rely on one model. Let a small team propose, then have an editor pull the best parts together. Who led the work?
The paper is led by Junlin Wang, with collaborators at Together AI and universities including the University of Chicago and Stanford. The conference version was recognized as an ICLR 2025 Spotlight, which signals strong community interest.
Nice. What problem are they actually trying to solve here?
Two problems. First, scaling a single model keeps getting more expensive. Second, different models have complementary strengths. Some follow instructions better, others write code more reliably, others explain clearly. The question is whether we can harness those strengths together at inference time without fine-tuning.
People have tried group strategies before, like ensembling or debates. What was missing?
Earlier approaches often route a prompt to one best model or re-rank multiple answers and pick one. That throws away useful information across drafts. Debate-style systems can help, but they add orchestration complexity and cost. The MOA approach is simpler. It treats other models' answers as input and tells a final model to critically synthesize a single, higher-quality response.
Walk me through how MOA actually works.
Think in layers. The first layer has several proposer models that answer independently. The next layer is an aggregator that reads the question plus all those drafts and writes a new, refined answer. You can add another aggregation layer if you want more polish. A key prompt tells the aggregator to evaluate, reconcile disagreements, and write a fresh response, not just copy or vote.
So it's like Mixture of Experts, but instead of routing tokens inside one network, you route full drafts among different models.
Exactly. The authors also observe collaborativeness. Many models write better answers when they can see other models' attempts first, even if those attempts are weaker. They find some role tendencies too. Certain models make strong proposers, others are strong aggregators, and diversity matters. A heterogeneous set of proposers beats sampling the same model multiple times.
What did they test and how did they compare fairly?
They evaluated on Alpaca Evil 2.0, MT Bench, and Flask, and in the conference version, they also reported Arena Hard. For Alpaca Evil, they used a length-controlled metric to reduce the usual bias toward longer answers. They repeated runs and reported averages and variation, and they analyzed quality versus cost and a compute-based latency proxy.
Which models were in the mix?
The default MOA uses only open-source proposers, models like Qwen 1.5, Llama 3, Mixtral, Wizard LM, and DBRX, and typically uses Qwen 1.5 as the final aggregator. They also tried a version with GPT-4 as the aggregator to check the upper bound, and a MOA Lite that trims layers and uses a smaller aggregator for better cost.
And results? How big is the lift, roughly?
On Alpaca Eval 2.0, the open-source MOA beat a strong proprietary baseline at the time of testing by a clear margin, think mid-60s versus high 50s on the length-controlled metric. On MT Bench, the gap is small because many top systems are near the ceiling, but MOA stays at or near the top. On Flask, it improves dimensions like correctness, factuality, completeness, and insightfulness. With GPT-4 as the aggregator, MOA also performs strongly on Arena Hard.
Interesting that the aggregator isn't just picking the best draft. Do they show evidence for synthesis beating selection?
They do. Actively synthesizing across drafts outperforms simply choosing one. The final answer tends to align more with the better drafts, which suggests the aggregator adopts strong ideas while still rewriting in its own words.
What about cost and latency? Multiple models talking sounds expensive and slow.
They plot quality against API cost and against a compute proxy and show a Pareto frontier. In plain terms, the right MOA configuration can match or beat single large models at similar or lower cost, especially the light setup. Latency has a catch. The aggregator waits for drafts, so time to first token is naturally longer. They suggest chunk-wise or streaming aggregation as a practical next step.
Any caveats I should keep in mind?
Yes. First, much of the grading uses LLM as judge. Alpaca Evil's length control helps and correlates well with human preferences, but automated judges can still encode stylistic bias. Second, reproducibility and drift. Reproducing the full setup requires access to several large endpoints, and model behavior and pricing can change. Third, most evidence is on instruction-following chat. The gains for long-horizon tool use or strict fact-checking under human-only evaluation remain to be established.
Fair points. Did they include ablations or checks to avoid lucky runs?
Yes, they reran experiments and reported means and variation, and they ran ablations on the number of proposers, diversity versus single-model sampling, and aggregator choice. The pattern is consistent. Diversity and a capable synthesizer matter most.
If I'm building a system, what's the Try It Monday version?
Start small. Pick 3 or 4 diverse open-source proposers. Use a strong instruction-tuned model as the aggregator. Give it a clear aggregate and synthesize prompt that tells it to critique and reconcile before rewriting. Measure on your real tasks, profile cost and latency, and begin with the light design if you need speed.
And for researchers?
2 directions stand out. Systems work to reduce latency with streaming aggregation and smarter scheduling. Only call extra models when drafts disagree. And learning work to distill the aggregator's synthesis into a single efficient model, or to automatically select the best mix of proposers and layers per domain. More human-grounded evaluations would also strengthen the case.
That's a clear takeaway. MOA treats models like colleagues. Let them draft independently, then ask a careful editor to produce the final answer. Simple, practical, and, based on the evidence here, effective within its tested scope.
Agreed. That's it for today's AI podcast. Thanks for listening, and if you try a small MOA setup in your stack, let us know how it goes.